In the quiet hours before dawn, when most of the world is still sleeping, thousands of people across the globe have made a decision that defies every survival instinct evolution has given us. They have volunteered, with full awareness and open hearts, to board a spacecraft bound for Mars, knowing they will never return. Not because of tragedy or miscalculation, but because the physics of space travel itself has drawn an invisible line in the cosmic sand. A line that says, you may cross, but you may not come back. Tonight, we will explore why. The journey to Mars has captured human imagination for generations. We have mapped its surface, landed rovers on its rust-colored plains, and analyzed its atmosphere molecule by molecule. The distance seems almost manageable now, roughly 140 million miles when the planets align favorably. With current technology, a crewed spacecraft could reach Mars in 6 to 9 months. A journey long but survivable, comparable to the great ocean voyages of centuries past. Engineers have calculated trajectories, tested life support systems, and designed habitats that could sustain human life on the Martian surface. But there is a problem, one so fundamental that it touches the very core of how physics governs motion through space. Getting to Mars is feasible. Getting back from Mars is something else entirely. This is not a matter of willpower or courage. It is not about better engineering or more funding. It is about the cold, mathematical reality of orbital mechanics, gravity wells, and the tyranny of something called the rocket equation. An elegant mathematical truth that reveals a disturbing fact. Every kilogram of fuel you need at your destination requires exponentially more fuel at your starting point. And Mars, for all its proximity and familiarity, sits at the bottom of a gravity well that demands an enormous price for escape. When we launch from Earth, we benefit from an infrastructure built over decades, massive launch pads, countless support systems, supply chains spanning continents, and staging areas where fuel can be delivered right up until the moment of ignition. Mars offers none of this. Any return journey must carry everything it needs or manufacture it from Martian resources, a technical challenge so complex that despite decades of planning, no space agency has demonstrated a fully functional system capable of producing rocket fuel on another world. The physics are unforgiving. To lift off from Mars, even with its gravity only 38% of Earth's, requires tremendous energy. That energy must come from fuel that must either be carried from Earth, adding crushing weight to the outbound journey, or created on Mars from local materials, a process that requires equipment, power, and chemical feedstocks that may or may not be reliably available. And this is just the beginning of a cascade of challenges that we will explore together tonight. Each problem compounds the next. Each solution reveals 3 new obstacles. The deeper we examine the physics of a Mars return mission, the more we understand why so many proposals quietly assume the journey will be one way. This is not a story of failure. It is a story of limits, the edges of what current physics and engineering allow. And perhaps, in understanding these limits, we can glimpse what it would truly take to overcome them. Before we drift deeper into these orbital mechanics and fuel calculations, I'd like to ask you something. Wherever you are right now, watching this video, take a moment and leave a comment. Tell us where you're watching from and what time it is. Are you settling in for the evening or greeting a new day? Are you alone with these thoughts or sharing them with others? This question of distance, of journeys we can and cannot return from, connects us all across this small planet. Let us know you're here. Now, let us begin. Let us trace the invisible forces that make Mars a destination we can reach, but may not be able to leave. The mathematics are beautiful, the implications are haunting, and the truth, as always, is written in the motion of worlds. Before we even speak of Mars, before we dream of red sunsets and distant horizons, we must confront something far more immediate and unforgiving. A mathematical truth that governs every spacecraft ever launched, every mission ever planned, every ton of cargo ever lifted from Earth. It is called the rocket equation, and it is not merely a formula. It is a fundamental law of the cosmos, as absolute as gravity itself, and far more constraining than most realize. This equation was discovered over a century ago by Konstantin Tsiolkovsky, a Russian schoolteacher who never built a rocket in his life, yet understood their limits better than anyone who came after. His equation is deceptively simple in appearance, but devastating in its implications. It states that the change in velocity a rocket can achieve, what we call delta V, depends on the natural logarithm of the ratio between its starting mass and ending mass, multiplied by the exhaust velocity of its engine. In simpler terms, the rocket equation tells us this: to go faster, you need more fuel. But that fuel has mass, so you need more fuel to carry that fuel, and more fuel to carry that fuel, and so on, in an exponential spiral that quickly becomes absurd. The mathematics are ruthless. Double your desired speed, and you may need 10 times the fuel. Triple it, and you might need 100 times more. The curve does not climb linearly. It explodes upward, quickly reaching masses that cannot be built, cannot be launched, cannot exist. This is why space travel is hard. Not because we lack ambition or technology, but because the universe itself places limits on what chemistry and mass can accomplish together. Consider the journey to Mars. Leaving Earth's surface requires approximately 9.4 kilometers per second of delta V to reach low Earth orbit. That alone consumes the vast majority of a rocket's fuel. The Saturn V, the most powerful rocket ever successfully operated, stood 363 feet tall and weighed over 6 million pounds at launch. Of that enormous mass, only 100,000 pounds, less than 2%, actually reached the moon. Everything else was fuel and discarded stages, burned away to overcome Earth's gravitational embrace. Now imagine the return journey from Mars. Here, the equation becomes even more unforgiving. To leave Mars's surface and enter orbit requires roughly 4 kilometers per second of delta V. That may sound modest compared to Earth, and in some ways it is. Mars has only 38% of Earth's gravity. Its atmosphere is thin, offering little resistance. But here is the cruel irony. Every kilogram of fuel needed for that return journey must be carried all the way to Mars in the first place, and carrying fuel to Mars is extraordinarily expensive. The journey from Earth to Mars, even using optimal transfer orbits, requires another 4 to 6 kilometers per second of delta V beyond what is needed just to escape Earth's gravity. Then, once at Mars, the spacecraft must slow down, shedding velocity to enter orbit or descend to the surface. More fuel, more mass, more tyranny. The numbers begin to cascade. Let us imagine a spacecraft designed to bring astronauts home from Mars. The return vehicle might weigh 10 tons empty. To accelerate that vehicle off Mars and begin the journey home requires perhaps 30 tons of fuel, assuming a reasonably efficient chemical rocket. But that means we must land 40 tons on Mars to begin with. Landing 40 tons on Mars requires carrying far more mass through interplanetary space, perhaps 60 to 80 tons, accounting for heat shields, landing engines, and the fuel needed to slow down in Mars's thin atmosphere. And here is where the equation truly bites. Every ton we wish to land on Mars requires multiple tons launched from Earth. Depending on the mission architecture, the ratio can be 10 to 1 or even higher. What began as a 10-ton return capsule has now become a 600-ton behemoth sitting on a launch pad, most of it destined to be discarded in the first few minutes of flight. This is the rocket equation's tyranny. It does not negotiate. It does not offer discounts. It simply is. Apollo understood this intimately. The missions to the Moon were exercises in mass optimization so extreme that engineers shaved grams from every component. The lunar module's walls were thinner than aluminum foil in places. Astronauts were given strict weight limits for personal items. Every ounce mattered because every ounce on the Moon required pounds in Earth orbit, and pounds in orbit required tons on the launch pad. And yet, even with this fanatical attention to mass, Apollo succeeded only because the Moon is close and has weak gravity. The delta-V requirements for a Moon landing and return are almost exactly at the edge of what chemical rockets can achieve with a single launch. Push the destination slightly farther, make gravity slightly stronger, and the equation becomes impossible. Mars sits beyond that edge. Earth's gravity well is deep, perhaps the deepest of any rocky planet in the habitable zone. Climbing out of it requires tremendous energy. Mars, by comparison, seems gentle. Standing on Mars, you would weigh barely a third of your Earth weight. Jumping would feel effortless. Lifting objects would seem easy. Yet even that diminished gravity is enough to trap you if you have not brought sufficient fuel. Here is what the numbers tell us. Launching from Earth to Mars is difficult but achievable with current technology. Launching from Mars to Earth is theoretically possible, but only barely, and only if everything goes perfectly. There is almost no margin for error, no reserves for emergencies, no backup plans that do not involve sending more mass, which triggers the equation's exponential spiral once again. Chemical rockets, the kind we have relied upon for every human spaceflight mission in history, face fundamental physics limitations. They work by expelling mass at high speed, typically between 3 and 4.5 kilometers per second for the most efficient engines. That exhaust velocity, dictated by the chemistry of burning fuel and oxidizer, sets an absolute ceiling on performance. We cannot simply burn fuel hotter or faster and expect dramatically better results. Chemistry has limits. Temperatures have limits. Materials have limits. Some fuels perform better than others. Hydrogen and oxygen, burned together, produce the highest exhaust velocity of any commonly used chemical propellant. But hydrogen is maddeningly difficult to store. It boils away slowly even in insulated tanks. It leaks through solid metal. It requires cryogenic temperatures that add complexity and mass. For a multi-month journey to Mars, and a spacecraft that might sit on the Martian surface for months or years waiting for a return window, hydrogen presents nearly insurmountable storage challenges. Other fuels, like methane or hypergolic propellants, can be stored more easily but offer lower performance. The rocket equation extracts a steep penalty for that convenience. Lower exhaust velocity means exponentially more fuel mass required for the same mission. There is no free lunch. Every choice involves compromise, and every compromise makes the return journey harder. The Apollo mission succeeded because they pushed chemical rocketry to its absolute limit within a very specific set of circumstances. The Moon is close. The launch windows are frequent. The delta-V budget, while tight, was achievable. NASA engineers could calculate fuel margins down to the kilogram and trust those calculations with human lives. Mars offers no such luxuries. The distances are vast. The launch windows occur only once every 26 months when the planets align favorably. The delta V requirements are higher, the timescales longer, the uncertainties greater. A spacecraft cannot simply carry a little extra fuel as insurance. Quote, becomes tons, which becomes tens of tons, which quickly spirals into mission architectures so massive they dwarf anything humanity has ever attempted. This is the tyranny we must accept before we speak of Mars colonies and interplanetary civilization. The rocket equation does not care about our ambitions. It does not bend to optimism or engineering cleverness. It is a law written in the structure of mathematics itself, as immutable as the speed of light. And it whispers an uncomfortable truth. Reaching Mars may be the easy part. Leaving Mars, returning home across the vast darkness, may require us to abandon the rockets that brought us to this point in history and embrace something entirely new. Or accept that some journeys are one direction only, not by choice, but by the cold mathematics of mass and velocity. After months of travel through the void, Mars appears as a rust-coloured beacon against the darkness. From a distance, it seems almost welcoming, smaller than Earth, gentler in appearance. Its gravity, measured at just 38% of our homeworld, might suggest that leaving Mars would be effortless, a simple reverse of the journey that brought us here. This assumption feels intuitive. Less gravity means less energy required to escape. The mathematics appear straightforward. But Mars is not straightforward. It is a paradox wrapped in red dust, a world that appears to offer an easy exit while quietly building walls around anyone who lands there. The numbers initially seem encouraging. Mars's escape velocity is approximately 5 kilometers per second, compared to Earth's 11.2 kilometers per second. On paper, this represents less than half the energy requirement. A spacecraft engineer might look at these figures and feel optimistic. After all, if we can launch rockets from Earth's deep gravity well, surely Mars should pose no significant challenge. But this calculation exists in a vacuum, both literally and figuratively. It accounts only for gravity, ignoring the complex web of factors that transform Mars from a simple equation into a formidable obstacle. The first trap reveals itself the moment a spacecraft attempts to land. Earth's thick atmosphere, which we often take for granted, performs an extraordinary service during descent. When a capsule plunges toward Earth at orbital velocities, friction with the dense air does the majority of the work. Parachutes deploy. Heat shields glow white-hot, converting kinetic energy into heat that dissipates harmlessly into the surrounding atmosphere. A spacecraft arriving at Earth can shed as much as 99% of its velocity through aerobraking alone, arriving at the surface having burned relatively little fuel. The atmosphere is an invisible assistant, one that works tirelessly without demanding payment in propellant mass. Mars offers no such luxury. Its atmosphere exists, technically, but calling it an atmosphere feels almost generous. At less than 1%, the density of Earth's air, the Martian atmosphere is barely thicker than the vacuum of space itself. It provides just enough resistance to create heat during entry, requiring heat shields and thermal protection, but not nearly enough to slow a spacecraft effectively. Parachutes deployed in Mars's thin air billow weakly, struggling to grip the gossamer molecules of carbon dioxide that constitute the planet's envelope. Engineers must design landing systems that use rocket propulsion for the final descent, burning precious fuel to cushion what Earth's atmosphere would handle freely. This creates a cruel symmetry. The atmosphere is thick enough to be a problem during landing, yet too thin to be a solution. Spacecraft arriving at Mars must carry fuel for powered descent, adding mass to the journey. That additional mass required more fuel to launch from Earth in the first place, which required a larger rocket, which required more infrastructure, each requirement cascading backward through the mission architecture like dominoes falling in reverse. But the true revelation comes when we consider the return journey. Standing on Mars's surface, looking up at the pale butterscotch sky, an astronaut might feel the lighter gravity as freedom. Walking is easier. Lifting equipment requires less effort. Muscles trained on Earth suddenly possess superhuman strength. Yet this same reduced gravity, this apparent gift, conceals the architecture of a trap. To return to Earth, a spacecraft must first escape Mars's gravity well. That 5 kilometers per second of velocity must be achieved, and it must be achieved without assistance. There is no thick atmosphere to launch through gradually, using wings and aerodynamic lift to gain altitude efficiently. There is no possibility of air-breathing engines that draw oxygen from the surroundings, reducing the oxidizer mass that must be carried. Every molecule of propellant, every gram of fuel and oxidizer must be brought from Earth or manufactured on Mars itself. The hidden cost emerges in the exponential nature of rocket physics. In space, every kilogram is not merely a kilogram. It is a burden that multiplies through the mission architecture. 1 kilogram of payload requires approximately 3 kilograms of fuel to lift it. But that 3 kilograms of fuel must also be lifted, requiring additional fuel, which must also be lifted, creating a recursive mathematical progression that grows savagely with each addition. Consider a simple thought experiment. A spacecraft sitting on Mars's surface needs fuel to reach orbit. That fuel has mass, which requires more fuel to lift. If we want to return astronauts to Earth, we must also carry fuel for the interplanetary transfer, fuel to slow down when reaching Earth, and life support systems to keep the crew alive for months of travel. Each of these requirements adds mass. That mass must be launched from Mars, which requires more fuel, which must be launched from Earth along with everything else. Now imagine that this fuel was not manufactured on Mars, but brought from Earth. The return vehicle, sitting on Mars's surface, represents a mass penalty that travelled through space for months. Every kilogram of return fuel was launched from Earth at tremendous expense, travelled to Mars burning fuel along the way, landed on Mars burning still more fuel, and now must be lifted back to orbit to serve its intended purpose. The thin atmosphere that made landing difficult now becomes a curse for departure. On Earth, rockets can achieve some aerodynamic efficiency during the initial climb through the atmosphere. The air provides something to push against, allowing fins and control surfaces to function. Launches can be optimized for atmospheric conditions. But from Mars, there is no such optimization possible. A rocket leaving Mars climbs through air so thin it might as well be absent, gaining no benefit, receiving no assistance. This is why Mars is often described as a gravity prison with thin walls. The walls are not insurmountable, they can be climbed, but they extract a price measured in mass, energy, and complexity. The 38% gravity figure is deceptive, a number that suggests ease while concealing difficulty. What matters is not the gravity in isolation, but the entire system of constraints. The thin atmosphere that helps with nothing, the absence of resources that could be harvested easily, the distance from Earth that makes resupply impossible, and the unforgiving mathematics of exponential mass growth. Comparisons with Earth reveal the depth of Mars's trap. When we launch from Earth, our atmosphere does half the work during landing, providing free deceleration. When we launch a rocket, we can use air-breathing engines for the initial climb, dramatically improving efficiency. Earth's magnetic field protects infrastructure from radiation. Earth's abundant water, oxygen, and industrial capacity mean that we never truly launch alone. We carry the support of an entire civilization. Mars offers none of this. It is a world stripped of conveniences, a place where every action must be carefully calculated because there is no margin for error and no external system providing assistance. The prison walls are thin, perhaps, but they surround you completely. And unlike a traditional prison, these walls grow higher the more you carry, the more you plan to do, the more ambitious your return journey becomes. Standing on Mars's surface, an astronaut must confront this reality. The sky above is reachable. The physics are known. But between that rusty ground and the safety of Earth orbit lies a gulf measured not in distance, but in sacrifice. Every decision made on Mars is shadowed by the question, can we afford the mass? And in that question lies the architecture of the trap itself. On paper, the solution to returning from Mars appears elegant, almost miraculous. Instead of carrying all the fuel needed for the return journey, we simply make it on Mars itself. The Martian atmosphere, thin though it may be, is composed of 95% carbon dioxide. With the right chemistry and sufficient energy, we can transform this atmospheric gas into rocket propellant. This is the promise of in situ resource utilization, or ISRU, a concept that has captivated mission planners for decades. It is a vision of planetary self-sufficiency, where Mars itself becomes the fuel station for our return voyage. But like many elegant theories, the gap between concept and execution is wider than the distance we travel to get there. The chemical process at the heart of this dream is called the Sabatier reaction, named after the French chemist Paul Sabatier, who won the Nobel Prize in 1912 for his work on catalytic chemistry. The reaction is deceptively simple. Take carbon dioxide from the Martian atmosphere, combine it with hydrogen, add heat and a nickel catalyst, and the result is methane and water. The methane becomes rocket fuel. The water can be split through electrolysis into hydrogen and oxygen. The oxygen becomes the oxidizer needed to burn that fuel. What remains can be recycled back into the system. On paper, it forms a nearly closed loop, a chemical perpetual motion that turns Martian air into the means of escape. SpaceX has built its entire Mars architecture around this assumption. The Starship, their massive spacecraft designed to carry humans to Mars, would use liquid methane and liquid oxygen as propellants. Upon landing, the empty fuel tanks would be gradually refilled, using Martian resources over the course of months or even years. When the launch window opens, when Earth and Mars align once more in their orbital dance, the spacecraft would lift off with tanks full of fuel manufactured entirely on another world. It is an audacious plan, perhaps too audacious. The first challenge is energy. The Sabatier reaction requires substantial heat to proceed efficiently. Electrolysis demands enormous amounts of electricity to split water molecules, liquefying methane and oxygen. Cooling them to the cryogenic temperatures needed for storage is an energy-intensive process that must continue day and night. On Earth, we accomplish these tasks with industrial facilities connected to power grids, drawing from fossil fuels, nuclear plants, or vast renewable energy farms. On Mars, there is no grid. There is no existing infrastructure. Every watt of power must be generated from equipment brought from Earth or assembled from Martian materials. Solar panels seem like an obvious solution. Mars receives sunlight. though only about 43% as intense as Earth due to its greater distance from the Sun. But Mars is also prone to planet-wide dust storms that can last for months, coating solar panels with fine red powder and reducing their efficiency to nearly zero. The Spirit and Opportunity rovers experienced this firsthand. Dust accumulation is not a minor inconvenience on Mars. It is an existential threat to any system dependent on solar power. Cleaning mechanisms add mass and complexity. Redundancy requires more panels, more mass, more equipment that must somehow arrive on Mars before fuel production can begin. Nuclear power offers an alternative. Small-scale reactors could provide consistent energy regardless of dust storms or the Martian night. NASA has developed the kilopower reactor, designed to generate around 10 kilowatts of electrical power. But a fuel production facility capable of filling the tanks of a Starship-sized vehicle would require far more power, possibly several hundred kilowatts running continuously for months. This means multiple reactors, each with its own mass, cooling systems, and safety requirements. Each reactor is another component that must function flawlessly, millions of miles from any repair facility. Each is another link in a chain where a single failure could strand the crew indefinitely. Then we encounter the infrastructure paradox, a logical trap that mission planners must navigate with exquisite care. To manufacture fuel on Mars, we need equipment, pumps to compress the thin atmosphere, chemical reactors to facilitate the Sabatier process, electrolysis units to split water, cryogenic coolers to liquefy the propellants, storage tanks capable of holding hundreds of tons of fuel without boil-off, power generation systems. All of this equipment has mass, substantial mass. To land this equipment on Mars, we need spacecraft with fuel. But if we had enough fuel to land heavy equipment, we might have enough fuel to simply carry return propellant in the first place. The solution, in theory, is to send the fuel production equipment ahead of the crew on separate unmanned missions. Let the robots set up the infrastructure. Let them begin producing fuel before humans ever leave Earth. By the time the crew arrives, months or years later, their return propellant is already waiting in tanks, ready to load. This is SpaceX's stated strategy. Send cargo starships first, laden with ISRU equipment and supplies. Give them time to establish the fuel depot. Only then send the crew, confident that their ticket home is already printed. But this introduces another layer of uncertainty. These unmanned missions must land successfully. The equipment must survive the journey and deployment. The systems must activate correctly, troubleshoot their own problems, and run autonomously for months or years. On a planet where communication delays mean a question takes 20 minutes to reach Earth and another 20 for the answer to return, real-time troubleshooting is impossible. The machines must be intelligent enough to adapt, yet simple enough to be reliable. They must function in an environment of extreme temperature swings, where night can bring temperatures plummeting to -100 degrees Celsius, cold enough to freeze carbon dioxide out of the atmosphere itself. Consider the timeline. Even under optimistic assumptions, producing enough fuel for a Mars ascent vehicle could take 12 to 18 months of continuous operation. This assumes perfect efficiency, no equipment failures, no unexpected complications. It assumes the thin Martian atmosphere can be compressed and processed at the necessary rate. It assumes the hydrogen feedstock, which must either be brought from Earth or extracted from Martian water ice, is available in sufficient quantities. Any delay, any malfunction, any miscalculation extends the timeline. And time, on Mars, is not merely an inconvenience. It is life support consumed, food reserves depleted, psychological strain accumulated. Every month the fuel production falls behind schedule is another month the crew must survive on finite resources. The Sabatier reaction has been demonstrated on Earth. It has even been tested aboard the International Space Station on a small scale. But operating an industrial-scale fuel production facility on Mars is not a laboratory experiment. It is chemical engineering in an alien environment with variables we can only partially predict. Martian dust is electrostatically charged and incredibly fine, capable of infiltrating seals and mechanisms. It is also mildly toxic, containing perchlorates that can damage both equipment and human health. Temperature swings could cause metal fatigue and seal failures. The low atmospheric pressure means that even small leaks can rapidly vent precious materials into the void. What happens if the fuel production system fails after the crew has already departed Earth? The journey to Mars takes 6 to 9 months. During that time, there is no turning back. If a critical component breaks, if production rates fall short of projections, the crew arrives at Mars to find their return ticket incomplete. Do they wait in orbit, gambling that repairs can be made remotely? Do they land anyway, hoping to fix the problem with hands that can work where algorithms cannot? Or do they face the unthinkable, acknowledging that the return may no longer be possible? SpaceX's confidence in ISRU is remarkable, perhaps necessary for maintaining momentum toward their Mars ambitions. But confidence and capability are not the same. The plan relies on a cascade of assumptions, each reasonable in isolation, but together forming a tower of dependencies where the failure of any single element jeopardizes the whole. It is not that the chemistry is wrong. The Sabatier reaction works. It is not that the concept is flawed. ISRU is theoretically sound. It is that the implementation in the unforgiving environment of Mars, with equipment that cannot be easily repaired and timelines that cannot be easily extended, is an engineering challenge of extraordinary difficulty. There is also the question of testing. Before we trust our lives to a fuel production system on Mars, we would ideally test it on Mars. But testing requires missions. Missions require funding, time, and risk. The first ISRU demonstration on Mars would itself be a historic achievement. Scaling that demonstration up to a system capable of fueling a human return mission is another leap entirely. We are discussing not a scientific experiment, but an industrial operation running autonomously on another planet. The difference between these two is the difference between a campfire and a power plant. In the silent Martian wind, beneath skies the color of rust, the fuel production facility hums with activity, or it should. This is the fantasy, the vision that makes Mars return missions appear feasible on mission planning charts and budget presentations. But fantasies, no matter how carefully calculated, must eventually confront the relentless physics of reality. The machines must work, the chemistry must proceed, the energy must flow. And if any part of this intricate dance falters, the astronauts who travelled so far may find themselves with a view of Earth in the night sky, a beautiful blue dot, impossibly distant, and no way to reach it. Beyond the engineering challenges, beyond the fuel calculations, beyond even the psychological preparation, there exists an invisible force that governs every journey to Mars and back. A force not of machinery or human will, but of celestial choreography written into the very fabric of our solar system. This is the realm of orbital mechanics, where planets dance to rhythms measured not in hours or days, but in years. And within this dance lies a disturbing truth. The universe does not care about your schedule. It does not wait for you to be ready. It offers windows of opportunity that open briefly, then close with absolute indifference. Miss your chance, and the cosmos will make you wait. The journey to Mars is not like booking a flight across an ocean. There is no departure whenever convenient, no alternative routes if you change your mind. The planets move according to laws older than Earth itself, and those laws dictate when, and only when, a return journey is possible. This is the invisible cage of orbital mechanics, a prison built not of bars, but of gravitational geometry and the relentless march of planetary motion. Every 26 months, Earth and Mars align in a configuration that makes travel between them feasible. This period, known as the synodic period, is the time it takes for Earth to lap Mars in their respective orbits around the Sun. Earth completes its orbit in 365 days, while Mars takes 687 days. Like runners on different lanes of a cosmic track, they periodically come close enough that the distance between them shrinks to a manageable span. But manageable is relative. Even at closest approach, Mars is still tens of millions of miles away, a gulf that takes months to cross even at tremendous speeds. During these alignment windows, spacecraft can follow what is known as a Hohmann transfer orbit, an elliptical path that represents the most fuel-efficient route between two planetary orbits. This elegant trajectory was calculated by German engineer Walter Hohmann in 1925, long before humanity had touched space. His mathematics revealed that the cheapest way to travel between planets is not to fly directly toward them, but to follow a curved path that gradually spirals outward from one orbit to meet the other. For Mars, this journey takes approximately 6 to 9 months, depending on the specific positions of the planets during launch. The Hohmann transfer is beautiful in its efficiency, but brutal in its constraints. It requires launching at precisely the right moment, when Earth and Mars occupy specific positions relative to each other. Launch too early or too late, even by days, and the spacecraft will miss Mars entirely, drifting past into the void or requiring massive fuel expenditures to correct course. The launch window itself is narrow, typically only a few weeks every 26 months when the geometric alignment is favorable. But here is where the invisible cage truly reveals itself. Once astronauts arrive at Mars, they cannot simply turn around and come home. The planets have continued their orbital dance, and the geometry that allowed the outbound journey no longer exists. Earth has moved far ahead in its faster orbit. To return, the astronauts must wait until the planets align again in a configuration suitable for the return Hohmann transfer. This means waiting on Mars, not for days or weeks, but for months. Typically, a surface stay of 300 to 500 days is required before the return window opens. Imagine the psychological weight of this reality. You arrive on Mars after a journey of 6 to 9 months, your body weakened by microgravity, your mind strained by isolation. You step onto the red surface knowing with absolute certainty that you cannot leave for over a year. The return window is not negotiable. It is not subject to emergency override. It is dictated by the positions of worlds weighing trillions of tons, moving through space at speeds of tens of thousands of miles per hour. No amount of urgency, no medical emergency, no change of heart can alter the cosmic schedule. And if something goes wrong during your stay on Mars, if the return vehicle malfunctions, if the fuel production system fails, if a critical component breaks that cannot be repaired with the resources at hand, then you wait another 26 months. The next return window will open, indifferent to your suffering, exactly when orbital mechanics dictate it will. 2 years and 2 months between each opportunity to leave. 2 years between hope and despair. The tyranny of the launch window extends beyond mere waiting. Each window is not identical. The distance between Earth and Mars varies dramatically, depending on where they are in their elliptical orbits. During some alignments, known as opposition-class missions, the planets are relatively close, making the journey shorter and less fuel-intensive. During other alignments, the distance is greater, requiring more time and energy. Some windows are favorable, others are marginal, and occasionally the alignment is so poor that mission planners simply skip that opportunity entirely, waiting for the next cycle 26 months later. Then there is the matter of delta V, the change in velocity required to alter a spacecraft's trajectory. The Hohmann transfer orbit minimizes delta V requirements, making it the most practical option for missions where fuel mass is limited. But it is also the slowest option. If you wanted to return to Earth faster, say in 3 months instead of 9, the delta V requirements increase exponentially. A journey half as long might require twice the fuel. A journey 1/3 as long could require 3 or 4 times the fuel. And remember, every kilogram of fuel must itself be lifted into space or manufactured on Mars, adding layers of complexity to an already monumental challenge. Some mission architectures propose faster trajectories using continuous propulsion systems or advanced nuclear engines. In theory, such technologies could reduce travel time significantly, perhaps even allowing for more flexible launch windows. But these remain theoretical. The physics is sound, but the engineering is decades away from reality. And even with such systems, the fundamental constraint remains. You must still time your departure to intercept Earth's orbit at the correct point. You cannot simply point your spacecraft at where Earth is now and fly straight there. By the time you arrive, Earth will have moved hundreds of millions of miles along its orbit. You must aim not at where Earth is, but at where Earth will be months from now when your trajectory intersects its path. This interplay of orbital mechanics and human vulnerability creates a profound existential tension. On Earth, we are accustomed to agency, to the idea that we can change our plans, that escape routes exist, that rescue is possible. But Mars strips away these comforts. The return window is absolute. The laws of celestial mechanics are inflexible. You cannot negotiate with gravity. You cannot petition the universe for an exception, and so the astronauts on Mars live within an invisible cage, not of walls, but of orbital geometry. They know the exact day, perhaps the exact hour, when the return window will open. They watch the calendar with a mixture of hope and dread, aware that if anything prevents them from launching during those critical weeks, they will remain on Mars for another 780 days. The psychological burden of this knowledge, the countdown to a single opportunity for survival, is unlike anything humanity has experienced in previous explorations. The invisible cage of orbital mechanics reminds us that space is not merely distant. It is governed by laws that do not bend to human need or desire. The planets move in their ancient rhythms, indifferent to the tiny vessels we send between them, indifferent to the fragile lives contained within. To journey to Mars is to surrender control, to place yourself at the mercy of a cosmic schedule written billions of years before you were born. And in that surrender lies both the terror and the truth of deep space exploration. We are not masters here. We are guests, moving through a universe that will continue its dance long after we are gone. We have crossed the vastness of space and arrived at Mars. We have endured months of confinement, radiation exposure, and the psychological weight of distance. We have landed on a world where the air is poison and the cold can freeze flesh in minutes. But now comes perhaps the most daunting challenge of all: assembling the means to return home. This is where the abstract mathematics of the rocket equation becomes brutally concrete. This is where every kilogram matters, where every decision carries the weight of survival. This is the mass budget nightmare. Imagine standing on the rust-colored plains of Mars, looking up at the vehicle that must carry you back to Earth. It sits before you, a towering monument to engineering precision. But what exactly are you looking at? What must this machine contain to tear itself free from Mars and carry human life across 140 million miles of void? Let us begin with the basics. The ascent vehicle itself. The structure, engines, fuel tanks, avionics, communication systems. Even stripped to absolute essentials, a spacecraft capable of reaching Mars orbit weighs tens of tons. The engines alone require materials that can withstand extreme temperatures and pressures while remaining light enough to be practical. Every strut, every wire, every rivet is scrutinized. Engineers speak of mass fractions, the ratio of fuel to structure, measured to decimal points that determine success or catastrophic failure. But the vehicle is just the beginning. Now we must add life support systems. Not the minimal life support needed for a brief journey, but robust, redundant systems capable of sustaining human life for months. Oxygen generation, carbon dioxide scrubbers, temperature regulation, water recycling. Each system is a web of pumps, filters, sensors, and backup components. Each component has mass, and here emerges a cruel paradox. The systems designed to keep you alive add weight, which requires more fuel, which adds more weight, which requires even more fuel. The spiral is relentless. The life support paradox extends beyond machinery. Human bodies are demanding passengers. An astronaut requires approximately 2 kilograms of water per day, minimum. For a crew of 4 on a 9-month return journey, that approaches 2 tons of water, unless recycling systems achieve near-perfect efficiency. Food presents similar challenges. Even the most calorie-dense, shelf-stable rations occupy space and add mass. A single crew member needs roughly 1 kilogram of food daily. Multiply that by crew size and mission duration, and the numbers become staggering. Then there is radiation shielding. Mars offers almost no protection from cosmic rays and solar radiation. The journey home traverses the same deadly environment as the journey there. Water can serve double duty as both life support and radiation barrier. But effective shielding might require lining the crew compartment with meters of material. Some proposals suggest using Martian regolith, packing tons of Mars dirt around the habitat. But now we face a question that haunts every mass calculation. How much protection is enough? How do we balance the certainty of added weight against the probability of radiation exposure? There is no perfect answer. Only trade-offs measured in millisieverts and kilograms. And what if something goes wrong? What if the launch window is missed due to mechanical failure, illness, or unforeseen complications? Mars and Earth align favorably for return journeys only once every 26 months. Miss that window and the crew must wait, not weeks, but years. Suddenly, the consumables calculation explodes. Food for 9 months becomes food for 35 months. Life support designed for one journey must endure multiple Martian winters. The mass budget does not simply increase, it multiplies catastrophically. This raises perhaps the most fundamental challenge. The ascent vehicle and supplies cannot travel with the crew. The physics simply does not permit it. Instead, everything needed for return must be pre-positioned on Mars, sent ahead on cargo missions, waiting on the surface when humans arrive. But how do we ensure that a spacecraft left dormant on Mars for months or years will function when needed? How do we protect it from dust storms that can bury equipment under meters of fine regolith? from temperature swings that range from minus 125 degrees Celsius at night to 20 degrees Celsius during the day, from the slow degradation of seals, lubricants, and electronics in an alien environment. The pre-positioning strategy introduces layers of complexity that ripple backward through the entire mission architecture. Every ton of equipment placed on Mars must first be launched from Earth, and launching mass to Mars is phenomenally expensive in fuel. Current estimates suggest that for every kilogram delivered to the Martian surface, approximately 50 kilograms must be launched from Earth orbit. The ratio is punishing. This is why serious Mars mission proposals, from NASA's Design Reference Architecture to Robert Zubrin's Mars Direct concept, require not one launch but many. Mars Direct, often cited as one of the most efficient approaches, proposes a minimum of 2 heavy lift launches per mission window. The first launch sends cargo, the return vehicle, habitat modules, rovers, and supplies. The second carries the crew. But even this streamlined approach assumes the development of spacecraft far more capable than anything currently operational. And 2 launches is the absolute minimum. More realistic assessments suggest 10 to 15 heavy lift launches would be required, each delivering components that must be assembled, tested, and integrated on another world. Let us consider the numbers more carefully. Studies estimate that a complete Mars return mission requires approximately 500 to 600 tons of equipment on the Martian surface. This includes the ascent vehicle, Earth return vehicle, habitat modules, power generation systems, rovers, scientific equipment, and all consumables. 500 tons. To put this in perspective, the International Space Station, assembled over more than a decade with dozens of launches, weighs about 420 tons. We are discussing the equivalent of building another space station, but on Mars, with far less infrastructure and support. Each component of this mass budget tells a story of compromise. The habitat cannot be too small, or the crew will suffer psychologically, but it cannot be too large, or it becomes unliftable. Rovers enable exploration and work, but each vehicle adds hundreds of kilograms. Scientific instruments expand our knowledge, but compete for payload capacity with survival equipment. Even personal items, photographs, books, small comforts that preserve sanity during years of isolation must be weighed against mission-critical hardware. There exists a deeper truth beneath these calculations. The mass budget nightmare is not simply about numbers. It is about the fundamental incompatibility between human fragility and the demands of spaceflight. We are biological beings evolved for one specific world, attempting to journey to another using machines that barely tolerate our presence. Every system added to make the journey survivable makes the journey more difficult. We are trapped in a recursive loop of requirements, each solution generating new problems, each problem demanding additional mass. Some engineers speak of elegant solutions, manufacturing fuel on Mars using atmospheric carbon dioxide and water ice, dramatically reducing launch mass. Building habitats from Martian resources rather than shipping them from Earth. Using nuclear power instead of solar panels to reduce mass and increase reliability. These concepts are not fantasy. They are grounded in real chemistry and physics. Yet each introduces new uncertainties, new technologies that must work perfectly the first time, millions of miles from any repair facility. The mass budget nightmare forces us to confront an uncomfortable reality. Bringing humans back from Mars is not merely difficult. It is an endeavor that pushes current technology to its absolute limits and perhaps beyond. Every kilogram must justify its existence. Every system must perform flawlessly. There is no margin for error, because there is no margin for mass. As we stand on Mars, looking at the vehicle that must become our salvation, we understand that it is not just a spacecraft. It is the physical manifestation of thousands of engineering decisions, each one a calculation of risk versus reward, protection versus practicality, survival versus feasibility. The vehicle is not merely heavy. It carries the weight of every choice that made the mission possible, and every compromise that made those choices necessary. This is the arithmetic of survival beyond Earth. Cold, precise, and unforgiving. We imagine the moment of departure from Mars as a triumphant reversal of the journey that brought us there. Engines ignite. Dust billows. The ascent vehicle rises on a pillar of fire, curving gently toward the black sky, and somewhere beyond it, home. In the animations, everything is clean, predictable, timed to the second. Reality would be nothing like that. On Mars, the dream of coming back is balanced on a thin stack of machines, assumptions, and probabilities. Each link in that chain has to hold. Each system has to work, not just once, but continuously, over years. The disturbing part is not that any single thing might fail. It's that every single thing must succeed. The first and most fragile of those links is the factory that's supposed to make your way home. In most plans, we don't bring return fuel from Earth. It's too heavy, too expensive. Instead, we send machines ahead, reactors, chemical plants, compressors, storage tanks, and ask them to do something humanity has never done anywhere but on Earth. Build a fully fueled interplanetary rocket from local resources on an alien world, with no one there to fix them if they break. Imagine landing on Mars knowing that somewhere over the horizon, on an empty plane, sits your lifeline. An automated fuel plant, quietly trying to turn Martian air and ice into methane and liquid oxygen. Pumps cycle, valves open and close, heat exchangers breathe in and out. Months pass, dust settles on panels, bearings wear. A software glitch, a frozen valve, a stuck compressor is not an inconvenience. It is the difference between a return vehicle with full tanks and one that is little more than a dead monument to hope. There is no fuel truck you can call, no spare plant over the next hill. If the fuel production system falls short, by 10%, by 1%, by a fraction, you don't get a slightly riskier launch. You get no launch at all. Even if the chemistry works and the tanks slowly fill, the next problem is more primitive and somehow more daunting. You need a place to launch from. On Earth, a rocket leaves from a pad carved out of tons of steel, concrete, and engineering tradition. On Mars, you're building that foundation from loose, electrostatically charged dust and fractured rock that has never known rain, never compacted under the weight of oceans or tectonic plates. It's a world made of powder and shards. A return vehicle trying to rise from that surface faces a cruel irony. The very act of launching could destroy the thing that must be perfect. Rocket exhaust will excavate the ground beneath it, blasting high-velocity grit into its own engines, tanks, and guidance systems. On Earth, this is handled with flame trenches, diverters, sound suppression. On Mars, you are trying to improvise a launch pad out of nothing. Do you sinter regolith with microwaves into hardened tiles? Do you land on inflatable mats or prefabricated plates dropped by earlier missions? Each approach is another system, another set of failure modes. Did the tiles crack in the cold? Did the deployment mechanism jam? Did the landing legs punch through a weak spot 3 years before anyone turns the ignition key? A launch pad is not just a slab of material, it is predictability. Without it, every ignition is a dice roll against erosion, imbalance, and cascading damage. Then there are the storms. Martian dust storms are not the towering ship-crushing tempests of science fiction, but they are relentless in their own way. Fine dust, sharpened by ages without weathering, creeps into every gap, coats every surface, blankets solar panels, and turns what looked like a clean engineering diagram into a dirty, abrasive reality. What happens when a regional storm rages for weeks, dimming the sun to a smouldering ember in the thin sky? The return vehicle sits in that gloom, its electronics cycling between cold and colder, its seals flexing, its mechanisms stiffening. The fuel plant, if it depends on solar power, may have starved for energy months earlier. Batteries discharge. Heaters shut down. Tanks, lines, valves get colder than they were ever tested for. You can design for storms on paper. Dust covers, redundant panels, wind load tolerances. But storms are not numbers. They are events in time. They happen when they choose, not on schedule. What if the storm hits during cryogenic loading, when valves must move and sensors must read with exquisite precision? What if sandblasting from wind-driven grit subtly scours a pressure line that, months later, ruptures under stress during ascent? On Mars, weather is not a backdrop. It is an active participant in your plan to leave. Even if the hardware survives, the factory, the pad, the storm, there is the most unpredictable system of all, the human body. On Earth, medical emergencies are frightening. On Mars, they are final. A burst appendix, a blood clot, a spinal injury from a fall in reduced gravity, an infection running out of control in a habitat with limited antibiotics and no intensive care. Each of these is plausible. None of them care that a return launch is scheduled 3 months, 3 years away. Evacuation is not a matter of hours or days. It is physically impossible. There is no rescue ship idling in orbit, no emergency launch window that can be opened at will. Orbital mechanics turns distance into destiny. When Earth and Mars are poorly aligned, the trip home lengthens from months to nearly a year. Even if a launch vehicle were magically ready and fueled the instant something went wrong, the patient would still be living on a clock set by positions of planets they cannot see. So mission planners must decide, in advance, what level of medical care is enough, when enough cannot be tested under real conditions. Do you bring an operating room, a blood bank, a CT scanner? Every kilogram of medical redundancy is a kilogram that is not fuel, not shielding, not life support. And if the worst happens anyway, the return ship becomes not a vehicle of escape, but a lifeboat that leaves some behind. Then there are the machines you brought to keep you alive, and the ones you will trust to take you home. A valve sticks on the oxygen recycler. A circuit board in the guidance computer fries after a cosmic ray hits at exactly the wrong moment. A seal on a high-pressure line ages faster than expected in the Martian cold, developing tiny cracks that are invisible until they become catastrophic. On Earth, we replace, we ship, we send technicians and specialized tools. On Mars, every replacement part must either be carried ahead of time or manufactured locally with equipment that itself can break. No one packlists an entire factory. No one knows which single custom gasket, chip, or bearing will turn into the missing bone in the skeleton of the mission. Even something as mundane as a missing bolt can become a showstopper if it happens in the wrong place. In microgravity, astronauts can sometimes improvise with tape, clamps, and creativity. On Mars, some things cannot be patched. A turbine blade eroded by dust, an engine injector clogged by contamination, a pressure vessel that passed all Earth tests but develops microscopic fatigue after endless freeze-thaw cycles in 1/3 gravity. You can design redundancy, but redundancy has mass. At some point, every mission confronts the same quiet compromise. Accept more risk, or accept that you cannot launch at all. Underneath all of these stories, fuel plants, launch pads, storms, surgeries, spare parts, is a colder, more unforgiving narrative. Probability. A return mission is not one gamble. It is a stack of them. Suppose the fuel plant has a 95% chance of working as intended. The launch pad and ascent vehicle, another 95%. The life support systems, 95%. The medical provisions, 95%. The communications, navigation, entry and landing system back at Earth, each at 95%. Individually, each sounds reassuring. Together, they multiply. You don't get 95%. You get 0.95 times 0.95 times 0.95 times. Again and again, for every critical subsystem that must not fail. Very quickly, your neat, optimistic percentage erodes into something more sobering. Add a storm that was worse than the model. A human error at the wrong second. A manufacturing defect no one caught. The numbers don't care how inspiring the mission patch looks. This is the tyranny behind the romance. The probability of success does not add across systems. It compounds. The more complex and ambitious the return plan, the more ways there are for it to unravel. None of this means we should not go. It means that when we talk about round trips to Mars today, we are often speaking in the language of intention, not yet in the language of demonstrated capability. The gap between those two is made not of feelings, but of physics, engineering, and statistics. And in that gap lies the question no animation, no press conference, and no glossy mission poster can easily answer. When you promise a crew that they are coming home, how many dependencies, how many untested systems, how many silent probabilities are you really asking them to bet their lives on? Long before rockets clawed their way out of Earth's gravity well, humanity learned something the hard way. Some journeys quietly stop being round trips. On the map, they are drawn as loops. In reality, they end as straight lines, fading into the unknown. When we talk about Mars as a one-way destination, it can feel unprecedented, almost unthinkable. But history is filled with moments when exploration slid into colonization, not by bold declaration, but by quiet inevitability. The ship could not go back. The ice closed in. The wind did not change. The physics of Earth, as merciless in their own way as the physics of space, made the choice for us. Consider Antarctica, a place on our own planet that might be the closest analogue to Mars we have ever known. A frozen desert, indifferent to human presence, where mistakes are punished instantly and mercy is a word without meaning. In the early 20th century, explorers like Robert Falcon Scott and Ernest Shackleton aimed to do what had never been done: reach the South Pole, then return to tell the story. On paper, they were round-trip missions. In practice, they walked a tightrope over a void of uncertainty. Scott's 1911 to 1912 Terra Nova expedition reached the South Pole after an exhausting march across the ice. They planted their flag, took their photographs, and turned back toward the coast. The plan still assumed symmetry: half the journey outward, half the journey home. But Antarctica does not respect symmetry. Temperatures plunged. Food ran out. Their bodies, weakened by months of exertion, could no longer match the demands of the distance. They had enough supplies to get there. They did not have enough margin to survive everything that went wrong on the way back. In Scott's final camp, just 11 miles from a depot that might have saved them, his team froze to death. Their return leg was not undone by heroism or cowardice, but by arithmetic. Calories, miles, temperature, time. An equation that no longer balanced. In those last days, the South Pole was not a destination visited and left behind. It became a boundary they had crossed, but could never recross. In effect, their exploration turned into a one-way journey, not by design, but by the cold logic of the environment. Mars imposes its own version of this, only instead of blizzards and ice flows, it is delta V, orbital windows and fuel mass. The numbers quietly decide whether round trip is real or just wishful thinking wrapped in familiar language. The same pattern echoes through early oceanic voyages. We often imagine explorers like Magellan, Columbus, or Zheng He as captains of grand loops across the globe, leaving and returning in stately arcs. Some did. Many did not. For some sailors, stepping onto the deck was closer to buying a one-way ticket than joining a temporary expedition. Storms, scurvy, shipwrecks, hostile encounters, mutiny. These were not distant possibilities. They were probabilities. The maps were incomplete. The ships were fragile. The ocean was a vast, moving void, with no rescue, no resupply, and no guarantee that the wind would ever blow you home. When sailors left Europe, or Asia, or the Pacific Islands, they often signed on for voyages whose advertised timelines were aspirational at best. "We'll be back in 2 years" was as much hope as plan. For many, the journey ended in unmarked graves under foreign skies, or in settlements that began as temporary trading posts and quietly hardened into permanent outposts. Jamestown, Plymouth, and countless other colonies were born from expeditions that blurred the line between exploration and settlement. On paper, some participants intended to return wealthy or at least alive. In practice, the distance, the cost, and the dangers meant that for many, it was effectively a one-way migration. Mars takes this historical ambiguity and amplifies it with physics. There is no rescue ship coming over the horizon, no lucky wind change, no passing whaler to ferry you home. Once you cross the Gulf to Mars, the ability to come back is not just difficult, it is a separate, massive mission of its own. What kind of person walks into that, knowing they may never stand on Earth again? History offers another clue. The psychology of the explorer. From polar parties to oceanic crews, there have always been individuals who accepted, sometimes calmly, that the odds of return were slim. Scott wrote farewell letters in his tent as he waited for death, framing his failure not as a miscalculation of courage, but as the price of pushing the frontier. Shackleton, in his famous and possibly apocryphal recruitment ad, summarized the deal with brutal clarity. Safe return doubtful. And yet, people lined up. The draw is complex. For some, it is the allure of firstness, to stand where no one has stood, to write the opening lines of a chapter in human history. For others, it is escape, from poverty, from war, from a world they no longer recognize as home. For still others, it is a deeper, almost inexplicable calling. To trade personal safety for participation in something that feels larger than a single lifetime. We saw a modern reflection of this during the Mars One project. Announced in the early 2010s, Mars One proposed something audacious. Establish a human settlement on Mars with no plan for return. No ascent vehicle, no waiting mothership, no transfer craft orbiting overhead. Just a one-way journey. Live on the planet. Die on the planet. The technical plan was widely criticized. Experts questioned its timelines, its life support concepts, its budgets, its engineering. The project ultimately collapsed under financial and practical realities. Yet one aspect of Mars One remains startling: the number of people who wanted to go. Around 200,000 applicants reportedly signed up for a mission that was explicitly advertised as one way, not as a temporary assignment, not as a tour of duty, as a final relocation to another world. They knew the risks were enormous. They knew the plan was speculative. Many knew the science well enough to recognize that failure was not just possible, but likely. But the idea of being among the first humans to step onto Martian soil was powerful enough to eclipse that. This raises an unsettling question for how we think about Mars missions in general. Is it more honest to tell people the return is unlikely from the start? Right now, most official visions of human Mars exploration are built around the round-trip model. Go there, stay for a while, come back. But as we have already explored, the physics make that tremendously demanding. Every kilogram of mass, every meter per second of required velocity, every launch window stacks the odds. Some argue that one-way missions are more aligned with those realities. If you do not have to bring people back, you do not need the massive ascent vehicle, the return fuel, the extra shielding, the redundancy in life support to survive both legs of the journey. Instead, you invest in building a permanent, self-sustaining outpost. You treat Mars not as a destination to be visited, but as a new shore to be inhabited. In this view, one way does not mean disposable. It means committed. The idea is not to abandon people on Mars, but to support them as settlers, not passengers waiting for a ride home. Historically, that is how many frontiers were actually opened. Rarely did early explorers simply touch land and sail away forever, only to return with a perfect report. They established bases, way stations, colonies. They adapted or died. The line between explorer and colonist blurred because the environment forced it to. But with Mars, this approach carries unique ethical weight. Is it acceptable to send humans on missions where coming back is nearly impossible, even if they fully understand the risks? Does informed consent have the same meaning when the dangers are so extreme and the uncertainties so vast? If we know that the physics make return extraordinarily difficult, do we have a responsibility to design missions as one way from the beginning, instead of promising a symmetry that may never materialize? Or is the opposite true? Should we refuse to send anyone until we can guarantee, within reason, that they can return safely? Should round-trip capability be a moral prerequisite for human exploration beyond Earth orbit? These questions do not have simple answers. They sit at the intersection of physics, ethics, and human desire. Some ethicists argue that as long as volunteers are fully informed and not coerced, one-way missions could be permissible, even admirable. Others worry about subtle pressures, the glorification of sacrifice, the romanticizing of martyrdom, the risk that economic or social desperation might push people into choices they would not otherwise make. History offers warnings on both sides. Lives were thrown away cheaply in the name of empire and profit. But there were also those who chose risk with clear eyes, reshaping what was possible for everyone who came after. Mars forces us to confront this legacy under a harsher light. Unlike the South Pole, unlike the New World, unlike any ocean crossing, a mistake on Mars is not a storm you can wait out, or a coastline you can stumble upon by accident. It is vacuum, radiation, toxic dust, and gravity that holds you just tightly enough that leaving again becomes its own monumental expedition. On a one-way Mars mission, there is no ambiguity. You are not going there and back. You are leaving one world for another and accepting that your story, however long or short, will end under an alien sky. In that sense, the physics of a Martian round trip do more than complicate mission design. They force us to decide what kind of explorers we are willing to be. Are we the kind who wait for guaranteed returns before we step forward? Or the kind who, like so many before us, accept that some doors, once opened, will not close behind us? As we weigh Delta-V budgets and launch windows, we are also weighing the value we place on a human life, the meaning of consent, and the price we are willing to pay to become a multiplanetary species. The numbers may tell us what is possible. They do not tell us what is right. That decision, unlike the orbits of planets or the pull of gravity, is still ours to make. If the physics of a chemical round trip to Mars feels like a locked door, this is the part of the story where we go searching for secret keys, ideas that promise to bend the rules instead of just obeying them. Technologies that whisper. Maybe the rocket equation isn't the final word. On paper, some of these solutions look almost magical. Nuclear engines that sip propellant instead of guzzling it. Spacecraft assembled like starships in orbit rather than stacked like fireworks on a launch pad. Trains of habitats on looping orbits that carry people between Earth and Mars without ever landing. They are real concepts, studied on whiteboards and in classified reports, sketched in margins by engineers who refuse to accept that impossible is permanent. They are also all missing the same thing: time. Not the cosmic kind measured in eons, or the orbital kind measured in synods between launch windows, but human time. The few short decades in which we are trying to go from first Mars landings to safe, routine round trips. Begin with a word that unnerves people for reasons that have nothing to do with physics: nuclear. Nuclear thermal propulsion is one of the most straightforward ways to cheat the tyranny of the rocket equation. Instead of burning chemical fuel and oxidizer together, you use a nuclear reactor as a furnace. Hydrogen flows through the reactor core, heats to blistering temperatures, and blasts out the nozzle. The result is simple but powerful: a rocket engine with roughly twice, sometimes even 3 times, the efficiency of the best chemical engines we have today. Higher efficiency means you can either carry less propellant for the same mission or go much faster with the same mass. In the context of Mars, that's not just a nice to have. It changes the geometry of the mission. A nuclear thermal stage could shorten transit time, reduce exposure to radiation and microgravity, and shrink the mass penalty of carrying a fully fueled return vehicle. The physics is not speculative. In the 1960s and 70s, under projects like NERVA, the United States actually built and fired nuclear thermal rocket engines in the Nevada desert. They worked. The exhaust roared out exactly as the equations predicted, but there's a difference between proving you can ignite an engine in the middle of nowhere and convincing the world you should launch one above a populated planet. Flying a nuclear reactor in low Earth orbit raises knotty political, legal, and ethical questions. What happens if a launch vehicle fails? How do you certify a reactor that will operate at temperatures and power densities far beyond anything in commercial nuclear power? Who gets to decide that the risk is acceptable? In space, the reactor's waste heat is easily radiated away into the vacuum. On the ground, the heat is political, hot, glowing, and radioactive in the court of public opinion. The result is that nuclear thermal propulsion exists in an odd limbo. Technically feasible, studied repeatedly, even funded in starts and stops, but never carried through to the scale and maturity needed to be the backbone of a crewed Mars program in the 2030s. If nuclear thermal rockets are about pushing harder, nuclear electric propulsion is about whispering for a very long time. Here, the reactor doesn't heat propellant directly. Instead, it generates electricity. That electricity feeds ion engines or Hall thrusters that accelerate xenon or other propellants to staggering speeds. The thrust is gentle, barely enough to feel. A paperweight would not budge on the engine bell. But in the vacuum of space, thrust doesn't need to be strong. It just needs to be patient. Ion engines have already proven themselves on missions like NASA's Dawn spacecraft, which orbited both Vesta and Ceres using little more propellant than fits in a carry-on bag. Their efficiency, specific impulse, is far beyond any chemical engine. For cargo, that's a superpower. A nuclear electric tug could in principle haul supplies and fuel between Earth and Mars orbit using a fraction of the mass. Yet there is a catch woven directly into the physics. Low thrust means slow acceleration. For heavy crewed vehicles that must depart and arrive in narrow launch windows, this becomes a major constraint. Designing a safe, human-rated nuclear electric system with megawatts of power, enormous radiator fields, long-life thrusters, and robust shielding is nothing like flying a small probe. It's closer to building a mobile space power plant, and then asking it to perform perfectly for years in deep space. We understand pieces of this puzzle. We have flown ion engines, experimented with high-power solar electric propulsion, and tested compact nuclear reactors in laboratories. But right now, a nuclear electric Mars transfer ship with humans aboard is still more architecture study than hardware. The materials, the reactors, the radiators, the redundancy, all of it would require a crash program on a scale that does not yet exist. If engines are one way to fight the rocket equation, changing where we put the fuel is another. Imagine this scenario. Instead of launching a Mars crew with all their return fuel strapped to their backs, we stock the route in advance. Orbital refueling depots in Earth orbit. Tankers slowly pushed to Mars orbit by efficient electric tugs. Pre-positioned propellant waiting like a cache of supplies left for polar explorers. SpaceX's vision of in-orbit refueling for Starship is the first step toward this idea. In principle, you can launch a mostly empty vehicle, top it off in orbit, and send it on its way. Extend that logic, and you get a network. Depots circling Earth, Mars, maybe even the Moon. Once the network exists, each trip becomes easier. You are no longer throwing away a perfectly good ship at the end of every journey. You are using space like a highway, not a cliff. The obstacle is that we don't yet have a highway. We have a handful of on-orbit refueling demonstrations, no permanent depots, and no large-scale cryogenic storage systems that have proven they can sit untouched in space for months or years without boiling away their contents. A Mars depot is more than just a tank in the sky. It is a piece of infrastructure that must be launched, assembled, serviced, and trusted with human lives. Like nuclear propulsion, the physics cooperate. It's the engineering, logistics, and time that lag. If depots are gas stations in orbit, cyclers are the trains. The Aldrin cycler concept is deceptively simple. Place a large shielded spacecraft on a particular orbit that repeatedly swings past Earth and Mars at predictable intervals. The cycler doesn't break or land. It just loops over and over like a planet-scale commuter line. Smaller taxis carry people and cargo up from Earth to rendezvous with the passing ship, then later back down from Mars. In this picture, the heavy shielding, life support, and radiation protection stay in space permanently. You don't launch them in and out of gravity wells. You treat the transfer itself as reusable infrastructure. It's a beautiful idea because it turns Mars travel from an expedition into a timetable. But cyclers demand exquisite timing and a level of orbital traffic that we simply don't have yet. The rendezvous maneuvers must be precise. The cycler must be built and maintained, perhaps for decades, and it doesn't actually remove the need for high-energy propulsion on the legs to and from the surface. It rearranges where you pay your energy debt, but it cannot erase it. Still, cyclers sit on the horizon like the first concept sketches of railroads once did. Ambitious, risky, and potentially transformative. But only after a more basic level of Mars access has already been achieved. If building starships in Earth's gravity is the problem, why not build them where gravity is barely there at all? Advanced manufacturing and 3D printing on Mars and in orbit promise to change another part of the equation, the vehicle itself. Instead of launching a fully finished return ship from Earth, imagine landing a set of compact, robust machines on Mars. Printers, metal refineries, robotic assemblers. Over years, they turn Martian regolith and imported feedstocks into pressure vessels, fuel tanks, even replacement parts for engines. The return vehicle is not launched, it is grown. There are early hints that this future is possible. We have 3D printed metal components for rocket engines on Earth. We have printed tools aboard the International Space Station from digital files. NASA and other agencies are experimenting with sintering regolith simulants into bricks and structures. Yet, between printing a wrench in microgravity and printing a human-rated interplanetary vehicle, there is an abyss of reliability, quality control, and complexity. Every weld, every seal, every composite layer in a spacecraft is the product of decades of manufacturing evolution. Recreating that sophistication on a new planet with harsh dust, limited oversight, and no possibility of quick rescue is not a 2030s problem. It is a mid to late century challenge. If even leaving Mars is hard, perhaps we can make that first step off the surface less brutal. On Earth, the steepest cost of going to space is not the journey between worlds. It is the first few hundred kilometers where thick atmosphere and strong gravity conspire to make rockets enormous and fragile. Mars is kinder, but not by nearly enough. Here, electromagnetic launch systems, the stuff of science fiction railguns and coil guns, offer a different vision. Instead of chemical combustion, you fling payloads along a track using magnetic fields, accelerating them to orbital or near-orbital speed. No propellant burned, no giant tanks, just electricity and engineering. In theory, a launch loop or railgun on Mars could hurl cargo and perhaps one day hardened return vehicles toward Mars orbit for a fraction of the mass and cost of rockets. Lower gravity and thinner atmosphere reduce the stress. The system could run repeatedly, feeding depots, cyclers, or assembly yards in space with the steady cadence of a conveyor belt. But the forces involved are immense. Human passengers do not tolerate dozens of Gs. Long tracks, mountain tunnels, precise aim, atmospheric heating. Each is a non-trivial problem. For now, electromagnetic launchers are at the seed stage, demonstrated in labs, used to fire projectiles in military experiments, not to loft delicately balanced spacecraft. On Mars, with no infrastructure, no power grid, and no heavy industry, it is still a sketch on future engineers' desks. Nuclear engines, electric tugs, refueling depots, cycler trains, printed starships, railgun launchers. None of these ideas are illusions. They are serious, studied, sometimes prototype concepts. In some alternate timeline in which we began in earnest 30 or 40 years earlier, perhaps the first crew to Mars would already be boarding a nuclear-powered cycler, meeting a return vehicle printed quietly in a Martian valley, refueled by propellant launched from an electromagnetic track. In our timeline, the 2030s are almost here. Designing, funding, testing and flying any one of these systems safely would be a major multi-decade undertaking. Doing several in parallel to the level of reliability demanded for human life is beyond any current program's schedule. And so, as launch dates creep closer, the uncomfortable pattern emerges. Our imagination races ahead, sketching elegant architectures that tame the physics. Our hardware lags behind, tethered to chemical propulsion, limited infrastructure, and missions that, when viewed honestly, start to resemble one-way bets. The future technologies are coming. The question is not whether we can build them, but whether they will arrive in time to rescue the first waves of Mars explorers from the harsh, simple reality of the rocket equation. For decades, the journey to Mars has been presented as a round-trip adventure. A bold leap, a heroic landing, a triumphant return. Posters, animations, and press conferences all carry the same quiet promise: we will bring them home. But the physics we have followed through this story whispers something different. Behind every glossy concept image and dramatic trailer, there is a spreadsheet. Behind every speech about boots on Mars in the 2030s, there are numbers that do not bend easily to human will. Engineers see not the red horizon, but mass fractions, delta V budgets, thermal margins, and abort scenarios that grow more fragile the farther you travel from Earth. This is where a quiet tension emerges. The world loves the idea of a Mars mission. The equations are far less sentimental. Public perception of Mars exploration is shaped like a movie plot. We have learned to expect a beginning, a middle, and an end. Launch, land, return, resolution. Anything less feels incomplete, even irresponsible. A one-way journey sounds, at first hearing, like a failure of compassion rather than a consequence of energy, distance, and gravity. Yet in design reviews and closed-door workshops, the conversations are rarely so cinematic. Here, engineers speak in careful conditionals. If we can pre-deploy enough mass, if the ascent vehicle is fully fueled and verified, if ISRU works at scale. Every if carries with it thousands of tons of hardware, years of lead time, and costs that rise faster than the velocity needed to escape Mars. NASA, as a public agency, cannot simply shrug and say, the first ones probably won't come back. By policy and by culture, NASA's official stance is unambiguous. Crewed missions must include a credible path home. The agency was forged in the shadow of Apollo, where "bring them back alive" was not a slogan, but a mandate. From Mercury to the ISS, every human mission plan has been built around return capability. Not perfect safety, that is impossible, but a designed, engineered, and funded way back. For Mars, that position becomes a kind of gravitational constraint of its own. If NASA proposes a mission where the return system is uncertain, incomplete, or deferred to future technology, it risks more than technical credibility. It risks political survival. Funding approval in the United States is not a law of nature. It is a recurring conversation in committee rooms, where elected officials must answer to voters who may never have heard of the rocket equation, but know exactly what it means to lose a crew with no way to rescue them. In those rooms, the idea of a one-way mission does not sound visionary. It sounds like a headline. Government sends astronauts to Mars with no plan to return. The story writes itself, and not in the way mission planners would hope. This is the quiet core of the funding problem. One-way proposals, however physically realistic, however aligned with the brutal constraints of mass and energy, do not inspire appropriations in the same way that round-trip heroics do. A one-way mission is structurally honest but politically fragile. It asks not just for money, but for society to accept that exploration sometimes means crossing a line you do not immediately recross. For most public institutions, that is a line they are not empowered to cross first. Private companies, however, live under different stars. They answer to investors and markets, not directly to voters. Their grand visions are constrained by physics too, but not by the same layers of congressional oversight and national symbolism. A private company can say, out loud, what many government engineers can only model in silence: that the earliest sustainable missions to Mars may look less like flags and footprints, and more like one-way colonization attempts. Some of these companies have already flirted with the idea in public statements and early proposals. They speak of settlers, permanent presence, and building a city, rather than missions with defined endings. The language is subtle but important. A mission comes home. A settlement does not have to. This does not mean private actors are reckless. They still face investor caution, regulatory scrutiny, and public backlash. But they have more freedom to say, we will send people who understand that they may never breathe Earth's air again. Without that statement collapsing decades of institutional trust in a single news cycle. And hovering above all of this is another invisible framework: the laws and ethics that govern how humanity behaves beyond Earth. International agreements like the Outer Space Treaty were written in an era when Mars was a distant dream. They speak of peaceful purposes, avoiding harmful contamination, and the idea that no nation may claim celestial bodies as sovereign territory. Later guidelines add layers about planetary protection, biological contamination, and the rights and safety of astronauts. None of these documents explicitly forbid a one-way mission, but they cast a long ethical shadow over the idea. If we knowingly send people to Mars with no feasible rescue option, knowing that a launch failure, a habitat breach, or a crop failure might leave them stranded in a slow-motion emergency, what duty do we bear? To them, to their families, to humanity's sense of itself? At what point does exploration become something uncomfortably close to abandonment, even if every participant volunteers with clear eyes? These are not questions that fit neatly into mission timelines or hardware diagrams. They belong to ethicists, philosophers, medical boards, and international councils, all of whom move on timescales slower than a launch window. So agencies thread a careful path. They speak of sustainable presence, stepping stone missions, and pre-deployed assets. They emphasize redundancy, abort options, and the eventual return of crews. The word one-way rarely appears, even when some of the underlying constraints begin to resemble permanent residency by default. The media, caught between audience expectations and the complexity of orbital mechanics, tends to simplify further. In news packages and documentaries, Mars is usually framed as the next Apollo, a grand replay with better technology and higher stakes. Dramatic animations show sleek ships departing Earth, touching down on Mars, then rising majestically back into space, all in a few seconds of visual time. The years of transit, the mass of propellant, the fragility of life support systems all compress into a smooth cinematic arc. This compression is not malicious. It is a byproduct of storytelling, but it has a cost. If the public mostly sees Mars as a place you go and come back from, like the Moon, they naturally assume that the main missing piece is political will or budget, not the sheer physics of escape velocities and propellant logistics. When missions are delayed or downscoped, it is easy to conclude that someone, somewhere, lacks courage. rather than that the numbers, for now, simply do not close cleanly for a safe, routine round trip. In conference hallways and closed workshops, however, scientists and engineers often speak with a different tone. Off-camera, many will acknowledge that the first humans on Mars may effectively be committing to an indefinite stay, even if the official plan includes a notional return date. They know how easily a single launch failure in the supply chain could push a crew's departure window out by years. They understand that once you are on the Martian surface, the physics that made getting there so difficult make leaving even more so. Some quietly predict that, when the history of Mars exploration is written, the first successful long-term habitats will be remembered less as missions and more as the founding of settlements, places where people arrived expecting to stay for a very long time, with return framed as a rare, risky luxury rather than a standard phase in the flight profile. They are not resigned. Many believe that future technologies, nuclear propulsion, orbital fuel depots, large-scale in-situ resource utilization, could eventually make round trips common. But eventually is not a launch date. It is an acknowledgement that the early chapters of Mars exploration may be written under harsher terms than the public currently imagines. This is the uncomfortable truth at the heart of our story. Space agencies avoid it not because it is unspeakable, but because it is not yet compatible with the promises they are expected to make. Elected officials prefer guarantees. Taxpayers prefer round trips. Press releases prefer simple arcs of triumph. The physics prefers none of these. It simply is. So the conversation stalls in a quiet compromise. Officially, we design for return. Unofficially, we know that the line between a planned round trip and a de facto one-way settlement may be thin, especially in the early years, when every kilogram is contested and every failure mode is amplified by distance. To live honestly with Mars, we will eventually have to live honestly with this tension. We will have to decide whether we are willing, as a species, to support explorers who travel beyond the point where rescue is realistic, not as victims, but as informed participants in a project larger than a single life. We will have to reconcile our desire for heroic homecomings with the reality that some of the most profound journeys in history did not end where they began. The physics does not demand cruelty. It demands clarity. And as we step toward a future in which a human footprint marks the Martian dust for the first time, that clarity may be the most important tool we carry, more essential than any rover, more precious than any return capsule we might someday assemble in the thin, rust-coloured air. Only by facing what the equations truly say can we decide, together, what kind of journeys we are willing to make, and what it will mean, in the deepest sense, to call another world home. We have walked through every invisible wall between Earth and Mars. Not monsters, not secret conspiracies, but something far more stubborn. Equations. The rocket equation that punishes every extra kilogram. Mars's gravity that is just strong enough to hold you and just weak enough to make launching home brutally inefficient. Thin air that cannot lift wings or shield you from radiation or slow you down gently without violence. Orbits that refuse to line up when we wish, forcing months or years of waiting. A mass budget that grows like a nightmare every time we say, let's add a little margin, just in case. None of this is personal. Physics does not care if a mission patch says return. Space does not promise round trip. Understanding these constraints is not about killing the dream of Mars. It is about saving it from fantasy. When we ignore mass, delta V, launch windows, and life support logistics, we are not being bold. We are gambling with other people's lives. Realistic planning, Accepting that a return may be impossible with near-term technology forces us to ask better questions. What do we really owe the people we send? What does informed consent look like when the universe itself is stacked against a ticket home? There will still be people who go. Somewhere on Earth right now, a child is looking up at the red dot in the night sky and quietly deciding, I'd go, even if I never come back. History suggests they might mean it. Polar explorers, sailors on wooden ships crossing unknown oceans, climbers who step into the death zone on Everest, all accepted odds that most of us would call unacceptable. A one-way journey to Mars would be the purest expression of that same impulse, to trade personal safety for the chance to carve the first human footprints into alien dust. But if they go, we owe them more than hopes and slogans. We owe them every possible breakthrough that could tilt the odds, even slightly, back in their favor. Some technologies would genuinely change the equation. High thrust, high efficiency nuclear or fusion drives that make Mars-Earth transfers faster and less fuel hungry. Reliable in situ resource utilization that can turn Martian ice and atmosphere into propellant, oxidizer, air, and plastic. Orbital shipyards assembling modular vehicles so we are not trying to build an interplanetary ark at the bottom of Earth's gravity well. Advanced radiation shielding and closed-loop life support that make years in space survivable rather than barely endurable. Even something as subtle as better predictive models of solar storms could be the difference between life and death. None of these are guaranteed. Some may never arrive. But they give us a direction. We are not powerless. We are apprentices of the same physics that currently cages us. In the end, not every journey is meant to loop back to its beginning. Some voyages change us precisely because they are one way. The first farmers did not return to the hunter-gatherer steppe. The first settlers in distant lands often never saw their birthplace again. If Mars becomes a chapter in the human story, it may begin not with a round-trip expedition, but with people who choose to become Martians, knowing that Earth will live on only in their skies and their memories. If you've stayed with this video all the way here, you're already part of that conversation. I'd love to hear from you. Where are you watching from? What city, what country, maybe even what time of night you're listening to this? Drop it in the comments and tell me, would you ever accept a one-way ticket to Mars? If you found this deep dive into the physics helpful or thought-provoking, consider liking the video so more people can find it, and subscribe if you want more explorations like this. And if you'd like to go one step further, you can optionally join the channel as a YouTube member. It's absolutely not required, but it does help support the time and research that go into making videos like this. For now, we remain here, bound to our blue world. But the equations are written, the paths are mapped, and somewhere out there, Mars is waiting for the first humans willing to live and perhaps never return under a different sun.